Hi, in this section, 5.7c, we're going to talk about the method of partial fractions. So remember, you should have reviewed the Introducing Partial Fractions handout that had definitions and guidelines, reviewed polynomial long divisions, and rewriting your integrand as a sum of partial fractions. Okay, so right now we're going to start out by giving the partial fraction decomposition of r of x divided by x squared plus x plus 1 quantity cubed times x plus 1 quantity to the fourth times the quantity x squared plus 1 times x. Notice that x squared plus x plus 1 and x squared plus 1 are irreducible quadratics, which means that they have no real zeros. Okay, so we're going to use our guidelines to rewrite this as a1x plus b1 divided by the quantity x squared plus x plus 1, and it's repeated, so we have to write this plus a2x plus b2 divided by the quantity x squared plus x plus 1 quantity squared plus a3x plus b3 divided by x squared plus x plus 1 quantity cubed. And then we're dividing it by x plus 1, that quantity to the fourth. This is a linear factor that's repeated 4 times, so our numerical coefficient for our numerator should be a constant. So we say plus c1 over x plus 1 plus c2 over x plus 1 squared plus c3 over x plus 1 cubed plus c4 over x plus 1 to the fourth. Now, we also have x squared plus 1, so that numerical coefficient for our numerator should be a linear equation. So d1x plus e1 divided by x squared plus 1, and then we're left with x there, so plus f1 over x. And that is the partial fraction decomposition of this rational expression. Okay, now let's look at an example where we are going to give the partial fraction decomposition of 1 over x squared minus 4, and then we're going to evaluate this integral using that partial fraction decomposition we got. So notice that 1 over x squared minus 4 can be rewritten as 1 over the quantity x plus 2 times x minus 2. Okay, now we know that our partial fraction decomposition is going to be a over x plus 2 plus b over x minus 2. But now we need to find out what a and b are. So we are going to use the zeros. So using the zeros of x plus 2 and x minus 2, which are negative 2 and 2, we are going to find a and b. Okay, so let's do it. Now, notice that in order for two expressions to be equal, so this is equal to this, that means their numerators must be equal. Well, we have to find a common denominator over here. So a little bit more work. We have rewriting the right-hand side. You have a times x minus 2 plus b times x plus 2 all over x plus 2 times x minus 2. And I only rewrote that to say that we have 1 is going to be equal to that numerator because our numerators have to be the same. So that gives us that we have a, not with the highlighter, we have a times x minus 2 plus b times x plus 2 is equal to 1. Okay, so now we're going to call this star so we don't have to rewrite it all the time. So in star, substitute x equals 2. When we do that, we're substituting that in here. So we get a times 0 plus b times 4 equals 1. So again, 2 minus 2 is 0. 2 plus 2 is 4. Okay, so this gives us 4b is equal to 1, or b is equal to 1/4. Okay, perfect. So now we need to find a. So let's find a. So in star, substitute x equals -2. We get a. We're substituting in -2 now, so that's -2 minus 2, which is -4. So a times -4 plus b times 0 equals 1, which means -4a is equal to 1, or a is equal to -1/4. So now we found a and we found b. Perfect. So all of that to say that we have the following. Hence, we can say that 1 over x squared minus 4 is equal to the -1/4 times 1 over x plus 2 plus the 1/4 times 1 over x minus 2. So we substituted that in here. Okay, now we have something that looks like we know how to integrate this, which is what we wanted to do ideally. So the integral of 1 over x squared minus 4 dx is equal to the integral of -1/4 times 1 over x plus 2 dx plus the integral of 1/4 times 1 over x minus 2 dx, right? Because the integral of the sum is the sum of the integrals. Okay, so this is equal to -1/4 times the integral of 1 over x plus 2 dx plus 1/4 times the integral of 1 over x minus 2 dx. And now you do a u substitution here with u equal to x plus 2. Then you'll be integrating 1 over u, which is, we know the antiderivative is the natural log of the absolute value of u. So that's going to give us -1/4 times the natural log of the absolute value of x plus 2 plus 1/4 times the natural log of the absolute value of x minus 2. Remember, because we do a u substitution here with u equal to x minus 2, take the time and write it out if you need to. And then we add our plus c. And remember your laws of logarithms. It says if you're subtracting two logs, it looks like it's a plus here, which it is, but you're subtracting this one. So that means we can rewrite this as 1/4, the natural log of the absolute value of x minus 2 over x plus 2, all of that plus c. And that's our final answer. Let's look at another example. Now we want to give the partial fraction decomposition of 1 divided by the quantity x plus 1 times the quantity x squared plus x plus 1, which is an irreducible quadratic. After we've found this partial fraction decomposition, we're going to evaluate the integral of 1 over x plus 1 times x squared plus x plus 1 dx. Okay, so similar process. We write 1 over the quantity x plus 1 times the quantity x squared plus x plus 1. That's going to be equal to the quantity x plus 1 is linear. This is linear, so our numerator should be a constant. So that's a over x plus 1 plus x squared plus x plus 1 is an irreducible quadratic. So our numerator should be a linear function or line, right? So bx plus c over x squared plus x plus 1. And then we are going to set our numerators equal to each other. But first, remember, find your common denominator. So that will give us a times the quantity x squared plus x plus 1 plus bx plus c times x plus 1 all of that is going to be equal to 1. Okay, now we know that our 0 here is negative 1. Okay, so we're going to call this star again, using the 0, x equals negative 1 in star, we get the following. We're substituting in negative 1 here, okay? So we get a times the quantity negative 1 squared plus negative 1 plus 1, all of that, plus b times negative 1 plus c times negative 1 plus 1, that equals 1. Well, this is 0, so all of that just disappears, right? Because we're multiplying it by 0, which now we can simplify here. Negative 1 squared is 1. 1 minus 1 is 0. 0 plus 1 is 1. So we get a here equals 1. So we found a. Okay, so we can go ahead and write 1 there if we wanted to, just to keep track. Okay, so now let's find b and c. So we have now, we're going to substitute a equals 1 in star. So that gives us, so in star, substitute a equals 1. That gives us 1 times x squared plus x plus 1, which is just x squared plus x plus 1. So you could drop the parentheses there. Plus, here we need to expand this. So we use the FOIL method. We get bx squared plus bx plus cx plus c. All of that is equal to 1. And I'm leaving some room there because I see we have an x squared here and a bx squared here. So what we're going to do is combine like terms, and then we're going to set our coefficients equal to each other. So this is really a 0x squared plus a 0x plus 1. Okay. Now, we have x squared plus bx squared plus x plus bx plus cx plus 1 plus c. So we did some rearranging and we simplified. Now we're simplifying or combining like terms. So you have 1 plus b times x squared plus 1 plus b plus c times x plus the constant 1 plus c equals 0x squared plus 0x plus 1. So now what we do is we set our coefficients equal to each other. Okay? So that's what we're going to do. And we're going to find out what b and c are. So let's do that. So we have 1 plus b is equal to 0. 1 plus b plus c is also equal to 0. That's this 0. And then we have 1 plus c is equal to 1. So this means b is equal to negative 1. Over here, we have 1 plus c equals 0. Subtract 1 from both sides. That tells us c is equal to 0. So we're done. We found b and we found c. So now we can write 1 over the quantity x plus 1 times the quantity x squared plus x plus 1 is equal to 1 over x plus 1, because 1 was a, plus b is negative 1, so we would have negative 1x plus 0. Typically, you would just write negative x as your numerator, and I encourage you to do that. I'm just doing that here so you can see where the coefficients came from, which means we have our partial fraction decomposition is 1 over x plus 1 minus x over x squared plus x plus 1. Now we have to integrate this. That's the second part. We want to evaluate this integral. So now what we're going to do is evaluate the integral. So the integral of 1 over x plus 1 times x squared plus x plus 1 dx is equal to the integral of our partial fraction decomposition, which we found to be 1 over x plus 1 minus x over x squared plus x plus 1 dx. We're integrating a difference, so that's the difference of the integrals. So that's the integral of 1 over x plus 1 dx minus the integral of x over x squared plus x plus 1 dx. Now, this part is just a u substitution with u equal to x plus 1 and du is equal to dx here. So this is going to be the natural log of the absolute value of x plus 1, technically plus a c, but we still have this chunk to integrate. So we're just going to hold off on that. So minus the integral of x over x squared plus x plus 1 dx. Now, what is the integral here? What is the antiderivative? So I'm going to show you now a little trick. So I'm going to do an aside, and we'll come back to that portion. So let's do an aside over here to figure out what this integral is. Okay, that's the aside. So the integral of x over x squared plus x plus 1 dx, that's equal to, we're going to put 1 in a nice way. So that's the integral of 1/2 times 2x over x squared plus x plus 1 dx. And then I'm going to bring that 1/2 out. So this is 1/2 times the integral of 2x over x squared plus x plus 1 dx. So notice, I didn't change the integrand. I just put the number 1 in. Okay, so now, just thinking, why are we doing this? If we zoom in on our denominator, x squared plus x plus 1, if we take the derivative of our denominator is 2x plus 1. So I'm going to try to get 2x plus 1 in our numerator so we can do a u substitution. But we'll be left with some other information that we'll have to take care of or find the integral of. But this is a nice trick of entering 1 in and helping us throughout this integration. So now we are going to have 1/2 the integral. So now I'm going to add 1 and subtract 1. Still didn't change the integrand. I just put in 0 now. So over x squared plus x plus 1 dx. So now we can rewrite this as 1/2 times the integral of 2x plus 1 over x squared plus x plus 1 minus 1 over x squared plus x plus 1, all of this dx, right? Because all I did was write 2x plus 1 over this. That's minus 1 over this. So now this is a difference of integrals. It's the integral of a difference, so that's the difference of the integrals. And we can do a u substitution here for that. So this is going to be 1/2 times the integral of this part, do a u substitution with u equal to x squared plus x plus 1, and du is 2x plus 1. So we get the natural log of the absolute value of x squared plus x plus 1 as its antiderivative, minus the integral of 1 over x squared plus x plus 1 dx. Okay, so it turns out that this integral can be written as this. That's our aside. Now back to evaluating our integral. We can take what we have from our side and rewrite our integral as the natural log of the absolute value of x plus 1 minus everything from the aside, so minus 1/2 of the natural log of the absolute value of x squared plus x plus 1 minus the integral of 1 over x squared plus x plus 1 dx. Okay, now distribute the negative 1/2 and we get the natural log of the absolute value of x plus 1 minus 1/2 natural log of the absolute value of x squared plus x plus 1. And we're distributing a negative 1/2, so that makes this plus 1/2 times the integral of 1 over x squared plus x plus 1 dx. Okay, so we're almost there. Now the question is, what is 1/2 times the integral of 1 over x squared plus x plus 1 dx? So the question is, what is the antiderivative of that integral? Okay, so what we're going to do is we're going to zoom in on the integral itself, and then we'll remember to multiply it times 1/2 once we figure that out. So we're going to do an aside, and we're going to do this aside right within the problem. So an aside. What is the integral of 1 over x squared plus x plus 1 dx? Now, this, we need to do a trigonometric substitution. So hold on, because now we have to write out some things. Well, we look in our denominator, we're going to have to complete the square here. So the integral of 1 over x squared plus x plus 1 dx is equal to, we're going to complete the square. So we're going to think of this 1 hanging out over a little bit, and we're going to take half of 1, which is 1/2. We're going to square it, we get a 4th. So that's 1 over x squared plus x plus 1/4. And we have to remember not to change the denominator, so we're adding the 1, and we also adding 1, right, 1, minus 1/4. So, okay, what did we do? We completed the square here, so we took half of the coefficient of x, which is 1. So that's 1/2. We squared it, we got 1/4. But we also have to subtract 1/4 there. So now remember dx. So we're going to group this together. This is going to be equal to the integral of 1 divided by the quantity x plus 1/2 squared. All of that, 1 minus a fourth is 3/4 dx. Okay, so now we have this 1 over x plus 1/2 quantity squared plus 3/4. So we're going to take u to be x plus 1/2. Then du is equal to dx. Now, remember that u is equal to a tangent theta in this case because we have this squared and we're thinking of this as a square, so we have to take the square root of both. So our a here is the square root of 3 over 2 times tangent theta. So remember, the square root of 3 over 2 comes from thinking of this as a square. So we have to take the square root of 3 over 4, which gives us the square root of 3 over 2. Okay? Now, du is equal to the square root of 3 over 2. The derivative of tangent theta is secant squared theta d theta. So right now, we have everything set up for our u substitution. Okay? So now, our trigonometric substitution. So this is equal to the integral of 1 over u squared plus 3/4 du. But we know what all of that is, right? So let's put it in here. So that's the integral of 1 divided by the quantity, the square root of 3 over 2, tangent theta, quantity squared, plus 3/4. All of that times du. And remember, du is here. So we're going to write times the square root of 3 over 2 secant squared theta d theta. Okay? Let me draw a little squiggly line here so you don't think to include that in the writing. Okay? Now, we square everything. And we get the integral of 1 over 3/4 tangent squared theta. Now we're squaring, remember? And then we have plus 3/4 times the square root of 3 over 2 secant squared theta d theta. And then what we want to do is we want to use the identity for tangent squared theta. Remember, we have that. So hold on one second. But we actually don't want to use the identity for tangent squared theta. Let's take a look here. You have 3/4 here, 3/4 here. Something beautiful happens. This is equal to the integral of 1 over 3/4 times the quantity tangent squared theta plus 1. Wait a minute, we know what that is. That's secant squared theta. But let's finish writing it. Let's not jump too far. This is secant squared theta. So 1 over 3/4 is 4/3, right? 1 over 3/4 is 4/3. So we're going to pull this 4/3 out. Remember, that came from 1 over 3/4. We're also going to, so what we're going to pull out is this and this. That's where the following comes from. Okay? And then times the integral of secant squared theta over secant squared theta d theta. So notice that this is secant squared theta and this secant squared theta is that. Well, now we're smooth sailing, right? Because this is equal to 2 times the square root of 3 over 3. That's simplifying the 4 and the 2. The 2 goes cancels here, leave 2 here. So you have 2 square root of 3 over 3 times the integral of d theta, which we know is just theta. So this is really 2 square root of 3 over 3 theta plus c. Now, what's theta? What is theta equal to? So up here, we did the majority of the work. So let's go back up here and figure this out. So u is equal to square root of 3 over 2 times tangent of theta. So another aside, within our aside, we have theta is equal to tangent inverse of u over square root of 3 over 2. And that's equal to tangent inverse of 2u over square root of 3. Okay? So we know u is x plus 1/2. So you can put the x plus 1/2 in here. So that's equal to tangent inverse of 2 times x plus 1/2, which you're going to distribute that 2 all over the square root of 3. So whenever you see me write it down here, you will see what we get whenever we distribute that 2 there. So it's 2 square root of 3 over 3 times tangent inverse, because we know what theta is. This is theta. So tangent inverse of 2x, because we're distributing the 2, plus 1, because 2 times 1/2, 2 times 1/2 is 1, all over square root of 3. Wait a minute. That means, well, wait a second. Let's not forget the plus c. So plus c. All of that to say that we figured out what this integral is. Now we can go back in and substitute that into this yellow highlighted up here. So now we're going to go back to our blue. So using this aside, we get that our integral is the natural log of the absolute value of x plus 1 minus 1/2 times the natural log of the absolute value of x squared plus x plus 1 plus 1/2 times 2, the square root of 3 over 3, tangent inverse of 2x plus 1 over the square root of 3. And we're going to say all of that plus c. Technically, that should be a 1/2 c, but we're being a little bit loose with our constant. So all you can do now is multiply this 1/2 times this. Well, that would mean that this 2 cancels with this 2. So our final answer would then be the natural log of the absolute value of x plus 1 minus 1/2 the natural log of the absolute value of x squared plus x plus 1 plus the square root of 3 over 3 times tangent inverse of 2x plus 1 over the square root of 3, all of that plus c. That is our final answer. So as you can see, using partial fraction decomposition to evaluate an integral can be somewhat involved, as you see with this example. But that's the beauty of integration. So just to summarize this section, there are several cases with integrating rational functions using partial fraction decomposition. 1, g of x is a product of distinct linears. What does that mean? We're thinking of f of x over g of x. So g of x is our denominator here. G of x can be a product of distinct linear factors. G of x is a product of repeated linear factors. G of x has irreducible quadratic factors, or G of x has repeated irreducible quadratic factors. And you can certainly have combinations Okay, so that's partial fraction decomposition. Have a great day.